that range. You're probably some sort of very highly distinguished specialist. You're in some high performance space. You know, you're really, a lot of expectations are being made of you. So we say, at any given period of time, we notice that the distribution up there is relative to the age characteristics, so there is a narrower window in which you are likely in order to be within that range. So initially we have low values here, something like, I don't know, maybe 16 or whatever, when people get their first job at Sonic or whatever, and they're, you know, waiting tables or car hopping or whatever, or, you know, picking up trash or summertime, you know, lifeguarding, whatever. Down here, they're not making much, okay? Matter of fact, 50,000 seems pretty optimistic for someone underneath 20 years old, but there may be some reality to that. However, we notice that there is a relatively symmetrical curve to the center of this distribution that shows that by the time you're in maybe mid-30s to 40s, you started to kind of plateau. What happens over here is actually that your likelihood of being in the next epoch category greater than 250 is now between 16 and let's say 27 or 28, something like that, almost zero, right? Almost no chances. We have no samples, we have no examples within that range to show us that someone could be in that category. So we're thinking about this as now changing the space and changing the representation of the data in that space. We've effectively created a cutoff, and now we're dealing with the density characteristics of the data above with both a regression analysis and a density, probability density likelihood. Notice that the function underlying that process is relatively complex. Do we think that there is enough justification, is there enough data in the greater than 250,000 space in order to really justify that fourth degree polynomial to fit it? I don't believe so, okay? So I think this is one of those things where I think the leverage graph already tells us that. I'll tell you why. Look what happens, look at the thickness of this leverage graph around the outside of this poly. It's saying my confidence on this is pretty low, pretty weak. It could be anywhere in this range. I'm just picking where I see the middle. What happens at the end of the process? We see there towards about 65, towards 70. What happens to the leverage graph? It blows up, it explodes in both directions. It could be anything at the end of that process. Part of this has to do with something we'll talk about in a minute. That is the tail behavior of high degree polys. If you ever play around with high degree polynomials, by the time you start adjusting small values to the system, they sort of tend to cascade in the effect of, it's like grabbing a snake and the end of its tail, you know, just really whips around. It can change polarity, it can change value by a lot, just as a result of that high degree characteristic causing a lot of inversion to those values at the end of the system. So when you have a high degree poly, you end up with a lot less confidence in extrapolation potential. So since there's a lot less confidence in the ability to extrapolate the likelihood of an individual to exist past the 60 space in 250,000, part of that is because of the fact that, well, we just don't have the data for it. We don't have the data to make any reasonable understandings of the next connectivity. Oftentimes we use the term support, and we're going to talk about the idea of a support with support vector machines, but we're saying there is no data to support this claim, this conjecture. There is no place for me to put my foot out on once I get out there. Once I get out there, I'm hanging out in the wind. You know, I'm unstable because there's no additional information to tell me what's going to happen next. Funny thing is, this graph actually indicates that after about 62 or 63, your likelihood of being in the group plummets dramatically. That's primarily an indication of this last sample in that high category group, because the last shift came from a high value indicating to a low value. So the plot, the function fit to that drop relationship. And it just kept that drop going down, right? Whatever it was doing previously is likely what it's going to continue doing in the next position. That's the reason why we say that the leverage graph relative to the poly as a fit indicator is that had there been one more value here that was anything more positive than the previous value, the indicator would have been a increasing function of likelihood after that point, right? But because of the fact that we see lower density or lower likelihood with remainder of samples at that point in time, plotting this space, determining what's going to happen next, creating an extrapolation for likelihood potential becomes a little less valuable. But we've actually treated this function, we've been talking, or we're talking about the idea of cutting things up based upon the relationship of age here, right? But we also have the capacity of cutting things off relative to a threshold of the output characteristic. Now we can treat two different ranges of the output range with two different functional understandings. So as long as you're separating it out, utilizing reasonable characteristics, and as long as you're verifying the operation with the appropriate tools, you should be able to build any degree polynomial function that is justified to express or understand the level of data space. But you're going to have to understand, we're going to have to understand a few things about how they work, right? So when we create new variables in the data space, we can re-express our understanding of the underlying approximation function as they are appropriate to the regions of interest that are active for that fitted function. Instead of utilizing an expression of something like overall accuracy, we can think about it from the perspective of saying how much an individual data point varies from the underlying function expressed within its range. Now, one of the things that's interesting about this is, let's say the data points sit very well within the range of some value here. They sit well within a range of a value here, right? And maybe in this last region, pretty aligned with what we're looking for. But we find that the variance for the data points over here seems a little higher, right? They're a little bit more spread out from the space. Why does utilizing a piecewise variance approximation make more sense within this particular graph? Let's just say that we were going to utilize a third order polynomial to fit this, which is about right. Right? We have increasing and then maybe some relationship of a second order parabolic and then another decreasing function toward the end. So we have a slight deviation in value toward the end of the system. But notice, the RSS in each of these regions is relatively low. But if I consider the RSS in this region, what is happening? I'm actually penalizing the adjacent regions for behavior that is asymmetric, right? Now we have strange behavior or odd variance characteristics within a certain range of the operation. So instead of utilizing a global variance perspective for fitted values, something like the residual sum of squares or the mean square error, which would effectively treat all of these functions or all of these regions in the same way as all one big polyfit, I'm going to utilize a point-wise variance assessment, right? From a point-wise to regional assessment. So variance for the fit is relative to the function within the range as described by the new underlying range of interest, okay? So the variance is not going to be global for all the entire fit function, but only for that particular subset of information I'm looking for here. And I can standardize this system to create an estimation of standard error for some localized variable, let's call it x naught in this case, such that f of x naught has something like the residual standard error for the localized variance within the range that we're going to call x naught, the new set of variables projected within the space. Yes?
Is that like calculating the confidence interval?
Essentially, it's understanding the capture capacity of that specific function for that specific range. Okay. Right? So confidence interval is very close to that relationship. The idea of the capacity or the likelihood of that particular range to be able to be provided within a certain degree of accuracy would be the summation of the pointwise variances for that local region. Okay. So we create multiple linearities, we create multiple local functions for those linearities, and as a result we end up with a slightly different assessment of the performance in that range. Now what it's saying here is that comparatively, we have one function that's operating largely concerned with its viability and capacity to model the data that is less than 250, right? I could still utilize all of the data in the system, but this data up here would do what? Really pull this off. It would make it really, it'd be unfair to this particular plot. Yes, so by treating it as if all these points up here are going to add to the sum of square error for this particular plot, what happens? We actually are going to stretch this whole thing up in order to try to make a regression that fits for all of that data. But by creating a new threshold and cutting it off, treating the lower region as one set of information, treating the upper region as a different set of information, and then plotting it in a different space with a different residual, now we have two separate functions that can each one be analyzed relative to the various characteristics of the data space they're interested in. At that point in time, we can either fit some relationship to some degree D, right, to a reasonably low value of flexibility, and in order to choose D within that system, we're going to utilize something like cross-validation. So we say, how many degrees of freedom do we need to work with to establish the operability of this particular function within this particular space? So since this function, right, back here on this last slide, we don't need as high dimensionality as we do for understanding and fitting well below a certain degree of accuracy for the 250,000. As I said previously, it kind of almost doesn't make a lot of sense that you do need that relationship, but we do see a cluster here that tends to indicate a slight elevation, and then maybe a little bit of a peak down here toward the end, a few values elevated that might indicate this little spike toward the end of the process. Now, like I said, I feel like this is a big stretch with respect to this data. But for a fourth degree poly to try to capture that particular behavioral characteristic, that's where we ended up with the minimum error for this system. So we want to choose a reasonably low value of D for any polynomial approximation. And polynomial approximation allows us to be able to develop different methods, different understandings for the entire range of values within them, right? But by creating two different dummy variables, two different value sets as a result of that relationship, we're effectively cutting it off along a different axis. We're cutting it off to be able to create values above this point relative to values below this point relative to this values. We can utilize something like a logistic regression process, which we're familiar with this relationship, and this is effectively what we've done for that probability density function estimate that was on the right-hand side, is we've created a exponential fit for that fourth degree or D degree poly in order to try to compute the operational bounds or the fit bounds for that legit scale relative to the probability or likelihood of a value within the entire range of input space being greater than the 250. What do I have to have? I actually have to have access to the density information outside of that 250. So you're creating now a classifier that is going to tell you whether you're likely to be above 250 or below 250. So the first plot is just characterizing you based upon the general trend, the general density trend. The second plot is giving you the information to distinguish whether or not you've gone above or below a certain value. This is just two different examples of how to treat the data differently based upon each of these assessments, conjectures, ideas that we're working with. We can do this separately on several variables, right? By doing so, we can stack them into a matrix format and separate out the relative pieces of the system after we've created a matrix understanding of variables and individual probability assessments or regression assessments. We'll talk about that, what we mean by that with respect to GAMs in a bit. As I mentioned previously, the problem with this, utilizing strictly poly for localized approximation, is they have notoriously bad tail behavior. They're whippy when you get out to the end of their strata. So they're bad for extrapolation. So if you want to use a high degree poly to be able to fit something, and you want to try to get your accuracy down, or excuse me, up, you want to get your error down, you're only going to be able to do so within the range that is largely most populated within the data space. If you want to understand what's happening in there, you can use a poly. If you want to understand what's happening next, you have to make sure you keep that poly degree down to an absolute minimum. Because if you erase that degree at all in order to try to capture variance over the entirety of the range, right? What we're saying here is, what happens every time that I add a degree to a polynomial? What's the first impact? I've mentioned this to you guys beforehand, but it's one of those things you kind of have to say over and over again. What
It fits
happens?
itself.
Say again?
It's overfitting itself.
That's a relationship that you
Yeah.
could make an assessment of if I was to give you something like performance divergence,
Yeah.
okay? Just adding a degree to a poly does not guarantee that it will overfit. I said that would be in a case when I add too many degrees to a poly. There are actually cases in which there is not enough dimensionality in order for a line to truly capture the variance in a system. The biggest impact of adding a degree to a polynomial is that it actually allows that function to do something that we may need in order to be able to model something relationship. It allows flexibility. What's the flexibility that happens when you add, so what happens at first order? First order is nothing, it's a line. There's no flexibility, right? First. What's the second degree? Parabolic, right? What's the third?
Squiggle.
Squiggle, yeah. Right? What happened to it?
Sorry, not very technical.
No, it's interesting, because let's think about it from this perspective. So if this is the first curvature up, this is the second curvature.
It's like it has the inverse.
Adding a degree, so what happens at forward? Every time you add a degree to a poly, it gets you the opportunity to be able to change directions.
Yes.
Yeah.
That's the only thing that happens. It gets to turn, right? So if a line doesn't get to turn, but a poly gets to turn, every time you add an additional degree to that poly, you're adding an opportunity for it to have a change in direction. We take the relationship of those as we derive that relationship or derivative to create a characteristic of the change in direction relative to the system. So the argument that I make is the more dimensionality you add to this, the more degrees of freedom, the more opportunity you have to fit localized variances. So if it was doing this up to this point in time, now all of a sudden it's doing something else, right? Guess what? Now it was doing this up to this point in time, now it's doing something else, right? It was doing this, now it's doing this, now it's doing this, right? Now it's doing this. The process of change at each of those points can be seen as saying that there is a localization upon which the data indicates that the generalized trend that was previously being understood by the model at the lower dimensionality now has to adjust to capture that variation in its relative level of performance. So in order to capture variance, in order to capture larger scale trends happening over time or over some data input space, we need to increase the flexibility. But the problem therein lies is that the more you increase the flexibility of this system, the more unstable its performance at each of these extrema becomes. Because they are less supported by the information that's inside the system's bases. Right? So higher degree polys allow us to be able to fit to higher and more complex systems operating with increased internal performance about relative changes of the value pairs or value relationships. And these systems can be extended out to multilinearities, right? So we're dealing with polynomial fits for first here just low dimensionality spaces, two-dimensional spaces. But these things can be used to create surfaces in higher dimensionality as well. But they are a little bit too structurally complex in order to be able to be utilized in many cases. So let's talk about the next operation, all right? we recognize that polynomial fits were maybe a little bit too weird and behaviorally complex. They were to work for many cases. And guess what? How much time have you guys spent in mathematics and you're kind of looking at it and going, oh yeah, this makes sense, right? But you go, yeah, even still, I don't really understand exactly what's going on there, right? How does it fit and change? It's not very understandable. The parsimony is low. High dimensionality polynomials changes in behavior is like a little past the scope of what we tend to be as little fourth dimensional entities able to understand, right? You have to be at least one dimension above it in order to be able to make a qualitative analysis of that system. So if we go anything past our three-dimensional human operating through time, fourth dimension, right? Get outside of 3D space, looking down at 2D, and it gets a little complex for us to run in a high operation. So we want to try to create stuff that is minimally complex, but yet still structurally descriptive. So the next system that was effectively derived was a system that's called a step function. Now, I like to say that this is basically as an extreme of an option as you can take. This is the hard left turn away from the functional approximation capacity of something like a fourth order poly, right? Because what is the functional relationship of values as stated within the range as given here? It's just the average of the values in that space. What does that indicate for us? It's just the bias term.
Oh.
There's no linearity here. We've gotten so far past any approximation that we have just said we gave up, and the best we can do was just the average, okay? Best we can do is just the average. Now what I want to crank back here is I want to show how this works. We said previously we wanted to treat these as a stepwise operation. This is the first relationship of treating this as a piecewise function, right? So it states that for C1, or cut one, right? One of the problems I don't like about this is I don't like this C here. The reason why they use this C is because they use cut C and R. What's the problem with using C, capital C? Classification, right? It's sometimes we just ran out of letters, okay? So I don't really know what to do. How do we run out?
We use
We've got
green,
more, we're not
we
using
use-
enough of it.
Let's use S.
Use S, okay? Yeah, well, no, there's, no,
Snip?
not S. Not S. No, S is a whole other thing, let's not use S. Let's just say it's C right now, we'll come up with a Greek letter in a minute to describe this. Okay? I know that
Okay.
seems dumb, but there's Greek, you know what I'm talking about, Ada?
Well, yeah,
Yeah.
but this is what I like about doing stuff in MATLAB is just being able to name something plainly.
Exactly, just say what it is.
Can't we
Right?
just
So
write that?
anytime you say CC, right, and then onto the right-hand side of it, you see an inequality, recognize that it's describing a cut point in that system. So it's saying I'm assigning this inequality, which is the identity relative to values of the matrix. Okay, so it's saying matrix values with assessment in the range X less than 35, non-inclusive, will be considered to be members of group C1. Likewise, group C2 describes those that are members of 35 inclusive and greater up to 50 non-inclusive will now be members of C2. Let's watch what happens in the next one. It says values of X for the inclusion of X greater than or equal to, including, right, inclusive of 65 is C3. Is that right? Let me zoom in on this for a second. We said 30, right? 30 to 50, let's go back up above. 35, right? And then 35 to 50.
Oh,
we
we
have
jumped.
30, 35, 50. Yeah, this is wrong, okay? This slide is wrong.
That should
That should be C4.
Yeah.
Yeah. Okay. I like to point this one out because I think ultimately it's one of those things, once you realize that it's incorrect, you kind of understand more of what's going on. So the reason why I don't fix it is because if I remember to point it out every time, that's a good thing, right? It helps you think. But what should C3 be?
Maybe 50.
So
Well,
let's
X
go back up
would
above
be
and look at the value.
Greater than or equal to, or greater than 50 and less than 60.
Notice 50 is not inclusive here.
Right.
So 50 would be inclusive in the next one, right? So the relationship would be that same function, C of 2 for I of 50 inclusive to 65 non-inclusive,
Okay.
right? So the reason why I make sure we indicate these are non-inclusive is because these are hard cuts. These are threshold level cuts, right? They're not fuzzy, they don't have dual stroke membership, and they're not probability based, so they don't localize for overlapping, okay? So if they're probability based, we wouldn't care about the cut functions. But notice something here that's interesting. I have a relationship of the same functionality from the first plot that has the dimensionality greatly reduced and slightly changes the regions of interest here. It's saying that your likelihood of being in the range of making over 250,000 increases to something like 0.25-ish, right? 0.025, because it's half to 0, or 0.05, yeah. So 0.025 is your likelihood of being included in the greater than 250,000 range between about 35, right, and 50. Then it jumps up to something like, I don't know, 0.027 or something for, 0.23 or whatever for a little while, and then drops quickly off after 65, right, down to, a mediocre, 0.01 or 0.015, something along those lines. Notice it's significantly less complex than our previous assessment, but far more generalized. It doesn't really characterize anything unique or special that's going on in this space. So what we do is we create a series of dummy variables, and that's what the C values are stored in this space. These are dummy variables that represent each of the groups of interest. We interact with these based upon valuations of inclusion or exclusion. Notice one of the things that's interesting here is that by utilizing the relationship of additional factors on their own bases, we can make the problem less structurally complex and thus easier for us to understand both the individual values and their interactions. So let's say that this is a relationship between the involvement of the year as well as the relative amount of money that someone's making. Which year the data was collected in would matter with respect to the averages or generalized trends to increase and decrease salaries during that period. I'll give you 3 examples. 2008, the housing market crisis of 2008. 2012, the relative mortgage and financial collapse, right? And then 2020, right? A period of time in which for roughly the next 2.5 years, almost no one had a relative salary increase because most of the companies had frozen based upon earnings issues. So only recently have people started to have additional increases in salary. So during those epochs, during those value spaces, the relative trends that we would have been experiencing, generalized increases, generalized values of assessments for your likelihood to be able to mature into the next earnings space were effectively frozen or remained somewhat unchanged during that period. So we would allow different linear operations for each range of functional values or each range of relationships for spaces as well as the relationship of the ages of the individual within that space. So by allowing different categories, we give ourselves a lot more opportunity to be able to understand these interactions. Let's first look at this relationship, and I'm going to say the idea of using C comes from right here. So within R, we use cut, and then we use C to describe where the cut values are. This indicates that there are 5 cut values, which means there are 6 ranges. So it is less than 18, 18 to 25, 25 to 40, 40 to 65, and 65 to 90, and then greater than 90. Now, notice a couple of things about this. You're used to seeing this as it relates to one specific area, and I think that area matters because as much as we think that as engineers and scientists, we don't care about the marketing and the business side of the system, let's be realistic with ourselves. If nobody wants to pay us for the things we build, there's no point in building them. So at the end of the day, you do have to have someone that's able to sell those things. You do have to have markets and in total. But what are we used to seeing the 18 to 25 demographic and those people within the range of 16 to 34, et cetera? Marketing, sales, visualization, a lot of the things that we do with respect to projections, capacity, and data analytics actually take into consideration that at certain epochs of your life, certain things change, right? By the time you hit 18, you're now reaching the age of majority. In America, you can vote, you can likely get your own job, you're graduating from high school. By the time you hit 25, right, if you go to college, you're probably, on average, you're the age of a college graduate or young, maybe home buyer, right? So each of these ranges becomes what with respect to a range of operation for your likelihood of being a both earner and a spender. It totally changes the paradigm. So we can't utilize the same understanding of behavioral and spending patterns that we were using previously. We now have to treat that range of values as its own systematic understanding because both your capacity and your behavior characteristics have changed as a result of both legal and sort of realistic constraint changes in that system. We utilize something called a knot, and that is the relationship of those cut points, where exactly we place those. And this term comes from I guess you could call it a naval term, right? It's from boat navigation, in which you have a rope, right? And you tie a knot in that rope. They used to use ropes, and they would tie knots in them at a certain distance apart from one another, and they would use those ropes to lower them down to the bottom of the river to analyze how far it was to the bottom of the river, right? The reason why I use this is because that little analogy will stick in your head, and you'll start to think about the idea of how far apart one knot is from another knot as describing a region of something like the depth from a boat, right? So how far away those elements are and the difference between whether those elements were. They used to call that demarcation on a line Mark Twain. And that's where Samuel Clemens got his nom de plume, right? Where he got his pen name to write the famous American novels about the Huckleberry Finn and all of the stuff that happened on the Mississippi River with riverboats. Is because they would throw that down, count the number of knots as they pulled it up, and yell Mark Twain, and they would say the twine had this many knots on it. That's how deep it is. The bottom of the river, so that we don't get our boat stuck as we're driving over top of it. All right. We create a system of piecewise polynomial operations, and within the range of operation, those piecewise systems function if and only if the value of x of I for that particular feature input is satisfied relative to that cut point C, right? The knot. The value that C is set to is effectively where that particular rope is cut in half, or where that rope is considered for the system. So for the first section, as it leads to C1, we're going to utilize this first function, B not 1, right? Notice here, we say B1, so this is the 0th beta, the bias coefficient for the first function for the first space. So this is the linearity, or the polynomial, that is related for that localized region. And likewise, function 2, or basis 2, or region 2, within that system, that is the right-hand half of the cut at that particular point in time. We'll talk about an idea of utilizing a relationship of continuity, but we're going to first talk about the idea of the reason why we need something that improves continuity. Spline systems are those that operate with relationship to a structural understanding on either side of a knot system. Let's look first at the idea of a cubic polynomial treated in a strictly piecewise way. I've created a single knot, K-N-O-T, right, relative to this system of age. So I have data from, 16 to 78 or whatever that I have, and I want to create two polynomials that fit to them. I'm going to constrain those two polys first to cubic order because I don't assume that they're going to change direction more than twice within that region. Here's an interesting idea or interesting characteristic with respect to that knot point setting is you want to select those knot points such that what is contained within that range of values between that Mark Twain, right? You want to create the relationship of the data as it moves through that space to only have a certain amount of variance or a certain amount of transition relative to the complexity of the polynomial you want to fit within that space. So if there's more transitions, if there are more changes than something like a cubic in the space, guess what? You need another knot. You need to put another one in there such that each of those bases are only going to attempt to be modeled by that relative degree of polynomial. Interesting thing is we realized, or we kind of discovered, that a cubic poly, right, this relationship of being able to change once in increase, right, and then to be able to decrease and then be able to increase again, was about as complex as you needed in order to represent almost anything within a reasonable basis space, right? If it changes more than once, then we probably need to consider it an entirely separate relationship, an entirely separate process. So this is the idea that underlies the notions of utilizing a cubic. We see this relationship here, decreasing, increasing, decreasing. Relationship is that first cubic. But notice something. What is the likelihood that you are making exactly like 110,000 at 50, and then all of a sudden you turn 50 and now you're making 35,000. Like you wake up, you go to sleep, you wake up, it's your birthday, and then your check just got a great big bump. No. We don't see that type of discontinuity in the relationship between systems. So attempting to model it in that way, attempting to treat it as if it is a discontiguous relationship is not exactly the best for us, structurally not the best. So we try to create an understanding or relationship to connect between these elements such that we might have something like continuity requirements satisfied. Now, continuous piecewise cubic imposes a constraint and says that as you're approaching the knot from one side and as you're leaving it from the other side, right, we're going to build a bridge from both shores. We're going to guarantee that they come together at the same point of the system. This just said set end to position as a constraint, right? Wherever I end for my run here, you start your run there. That's the way in which a continuous operation works. But it creates this little, I like to call it a graph butt, right? It's a little graph butt, okay? Where you have something coming in and going down, and then all of a sudden it's coming out and up. There wasn't any flow to that process. Just a little cleft there where those two things came together. Also, not incredibly realistic and not great overall. Linear spline relationship, I'm not going to look at that. We understand what would happen there. If we set the constraint relationship to where two linear systems, that would just create the requirement for the intercept of the second plot to be equal to the intercept of the first as it approached the knot point. But the cubic spline process for continuous operability allows us to be able to set a relationship between the knots as they cross over this set point by establishing a relationship of the characteristics of each of these cubic polynomials as they're going through their own spaces. I'm going to step forward a minute, I'm going to show you this, and then we're actually going to move back into this in a minute. But this is the relationship that we utilize to be able to create smoothing operation as it relates to cubic splines, right? The natural cubic spline system. On the right-hand side, we have a lambda. We've seen lambda before. What do we use lambda for?
L1.
Rigid regression.
Correct. You guys are all right. Okay. But what do we call it? Cost penalty.
Yes, cost penalty,
Okay. So I'm creating a penalty. I was scaling. What do I have over here? Error, all right? My goal function is to minimize error. So if I add on to error something, over here it says, I've added on an additional penalty. I'm penalizing you. What am I penalizing this against? Penalizing it against the second derivative of that function.
Oh.
What would happen, what is the
Yeah.
second derivative of the function? So the first derivative is the change in direction, right? Change in value. What's the second? The change in the change of the value.
Wait.
I'm going to tell you this is cool. We'll talk about this on Wednesday. With this process, we can effectively turn a cubic polynomial back into a linear operation if we make lambda big enough.
Huh?
Remember how I said that you could force something, right, effectively
Yeah.
towards zero with regularization.
Yeah.
What happens if I regularize according to beta of the second and third order elements? The first order element does not have any second derivative, right? Lines don't have a second derivative. What's the second derivative of the square? The first order element. What's the second derivative of the cubic, right? That becomes the first element, first order element. So I have a change in value. Guess what? I can say, first of all, I need my marker again. I'll show you real quick how this works. If I increase the penalty, if I increase lambda, I would force this model to try and fit with less and less functional degrees of freedom. Eventually, this system would get so penalized that it would end up becoming a linearization of the relationship, right? I say, every time you change direction, every time there is a change in the change in direction, I'm going to penalize you. I'm going to regularize you. I'm going to force you down. As lambda goes toward infinity, the system effectively ends up back towards a linearity. But as lambda is anything less than an infinite value, effectively an infinite regression scale penalty, we can have a little bit of flexibility. So I can add a degree of rigidity to that flexible system, right? Everything doesn't have to be, I don't have to have everything being totally fabric, right? I can have something that has a little bit of constrained rigidity, right? It has some constraints in the system. I'm adjusting the flexibility of the surface by making it a little bit more plastic, making it a little bit more structurally rigid, okay? We'll talk about this as we get over next time. I'll let you guys go. Thank you very much. We've got, I'm going to, trees work effectively the same way this does. They're just able to do so on a sequential basis, right? They create cut points and set points, and then SVMs are totally out of this world, okay? They don't work the same way any of the other stuff we work does, so they're a neat trick. But I can show you a lot about how they operate visually. So Wednesday we're going to do trees, and then Friday I'll show you guys some visualizations and some tools to show you how those SVMs operate. And that should give you all the tools remaining in your tackle box in order to be able to tackle most kind of constraints and problems we're going to in space. So I'll try to give you guys some study guide material this week for your final. I'm working on putting together the remainder of that quiz. I should have that for you pretty soon. All right? Thank you very much, guys. I will see you on Wednesday.
If you have a second, real quick.
Oh, sure.
This isn't on the class tomorrow, but I'm trying to plan ahead to get homework done. And so this one here, I did it two different ways. Family stuff and other stuff. I just want to try to get it done.
I tried to get it out.
That was well, that's what I did all week. So this one here, the reliability is getting